Okay, welcome to our video on electrical power. Now you guys are at an advantage because we already talked about power during the energy unit. You'll recall that power, this is the one where we did the lab where we ran up and down the stairs with the backpack on and calculated our power. Power is equal to the work done divided by time. Okay, very straightforward. P equals W over T, and the definition is the rate of work done, or an alternative way to think of that is the rate of the energy change per unit of time. Okay, now this would be what we would call mechanical power, okay, when we did this before, okay, figuring out the power of like an object actually moving and changing its energy and dividing by time. Now, circuits are used to transport energy from one spot to another. So what we can do is we can determine how much power they dissipate or how much power they give off, the rate at which the work is done, the rate at which the energy is changed from electrical potential energy into heat energy or light energy or some other type of energy. What parts of a circuit give off energy and therefore dissipate some power? Well, basically comes down to anything with a voltage drop. Anything that has a voltage drop gives off energy. Okay? Because a voltage drop means that the energy divided by the amount of charge carrying that energy decreased. That's what a voltage drop is. So resistors, they give off some heat. That's how they give off their energy. So they dissipate power. Light bulbs, they give off both heat and light. And even wires themselves can give off some power. There's some energy loss or energy transfer at wires. Remember that wires don't have huge resistances, so they don't have huge voltage drops, but they do give off small amounts of heat. Tiny amounts of heat. Now, as far as the simulation goes, it doesn't show heat being given off, but since we know that voltage drops occur at resistors, we know that some energy is being given off. There must be some power being dissipated by this resistor. Some energy is being given off over time. With the light bulb, we can actually see how much brightness, how much light energy is being given off by these lines here. The bigger and more, the longer the lines in this simulation, the more energy is being given off. So if I like turn up the voltage here, you'll see that the light bulb gives off more and more and more energy, giving off tons of energy, giving off very little energy, like this. Okay, so so we can calculate power ratings. And since we talked about wires, if the wire resistivity is not 0, that's under this advanced column down here. If the wire resistivity is tiny, the voltage drop is 0, but if I increase it, you'll see that the wire has a voltage drop, therefore it is giving off energy. Okay. Let's go over some of the equations for power, and I'm actually going to do this a slightly different way. We're going to use this equation, and I want you to recall a couple of things. Let's start from this. And we know that the power is equal to the work done divided by time. By the way, units of power are watts. That's also capital W, so make sure you've got work and watts straight. We know that when a charge moves through an electric field between two different points, there's a potential difference. And we linked that to how much work was done by that charge, how much energy was given off. The work done is equal to Q times V, if I just multiply the Q up there. So I could change this to Q times V, and then look what I have. I have Q over T. I have charge over time. In other words, you could think of this as how many charges are passing by a certain point in a certain amount of time. Isn't that the definition of current? So I have V times I, and that's the foundational equation for power that we're going to use. The power developed, or the power given off by some component of a circuit, is equal to the voltage drop for that component multiplied by the current. But that's not the only equation for power. I also want you to think of Ohm's law. Remember that Ohm's law is this. V equals IR. Now, what if you don't know the voltage drop for a circuit component? Well, since you know V equals IR, you could plug in P equals, let's see, I times R times I, which gives you an equivalent expression for power of I squared times R. That also works. Another way you could think of this, what if you didn't know the current? Well, if you didn't know the current, we know that current is equal to V over R, just rearranging from Ohm's law. So this could be written as P equals V times V over R, which means that power is also equal to V squared over R. So the key here is based on the given variables, there are multiple equations for power. Can solve for P or anything else. Okay, and all those power equations are located right here. Power equals V times I, voltage drop times current, I squared times R, or V squared over R. And if we know an object's power rating, notice that power is equal to work over time, amount of energy over time. We can figure out, if we know the power, how much energy is released per unit of time. And that's useful if we have to pay electric bills. We want to know how much we're going to be paying, and we need to know how much energy we're using, how much power we're using. So, if P equals work over time, then that work, or in other words, the energy that's used, must equal the power over the time, where the W equals work done, or in other words, the energy transferred. Therefore, we can just take the equations for power and plug them in here and figure out how much energy was actually used, or how much energy was transferred. The work done, the energy transferred, equals power times time, which means I could have VI times T, I squared R times T, or V squared T over R. Each one of these equations works. And you don't have to memorize these. They are right in the reference tables for you, right here. Okay, that is actually everything on the electricity section. You've now gone over the whole thing. Okay, number one, a certain resistor has a voltage drop of 4 volts and a current of 0.2 amps running through it. What's the resistance of this resistor? Has nothing to do with power, straight up Ohm's law question. V equals IR. The voltage drop is 4 volts. The current is 0.2 amps. Make sure that we're getting the units right on these. The resistance, therefore, must be 20 ohms. We're going to go to the simulation to see that real quick. There's a 4-volt battery, a 20 ohm resistor. I'm going to bring over my ammeter, figure out what the current is. It's 0.2, just like we said. Okay, back to this question. What is the power dissipated by this resistor? There's multiple ways to do this, but for me, I'm going to go with the variables that we're given. We were given the voltage drop and the current, therefore the power must be V times I. Power is therefore 4 volts multiplied by 0.2 amps. 4 times 0.2 is 0.8, and the units are watts. If the resistor dissipates power for 28 seconds, how much energy is released? Well, if we need to know how much energy was transferred, energy was released, how much work was done, we use this equation. We now know the power and we know the time. The work done equals power times time. 0.8 watts times 28 seconds. 22.4 joules, because remember, a watt is a joule per second. Joules are released in that 28 seconds. That's how much work is done, how much energy is released. Okay? Very straightforward. Number 2, an electrical appliance draws a current of 0.5 amps and has an electrical resistance of 120 ohms. If it operates for 30 seconds, how much energy is released? So let's see here. We know the current, we know the resistance, and we know the time. We need to know the energy, how much work is done, how much energy is released. Notice that part B says, what's the power consumed? Well, some people want to do B first. That's fine. You don't have to. You can kind of do either one. I'm going to start with A, though. We're looking for how much work is done. We have the current, the resistance, and the time. I look on my reference tables, because I don't know the equation off the top of my head, and I see, okay, current, resistance, time equals work. That looks like a winner to me. Work equals I squared RT. 0.5 amps squared times the resistance of 120 ohms times 30 seconds. The amount of energy that's released is 900 joules. What's the power consumed by the appliance? We could do this just based on I and R, but this time I'm going to use the value we just found. The power is equal to the work done over the amount of time. Work done is just the energy transfer. That's what we just found up here. It takes 30 seconds. 900 joules divided by 30 seconds gives us 30 watts of power. Now, I could have also found that by doing I squared times R. 0.5 times 0.5 times 120 is 30. All right. More and more in this class, and more if you continue talking about physics and taking physics classes, you're going to see problems that don't require numbers, that don't have any numbers, and your job is to reason about them, even if they don't give you numbers. Doing that will build your conceptual understanding so that you don't have to rely on math all the time. You can just intuitively understand how something works. If the resistance of a constant voltage circuit increases, what happens to the power developed by the circuit? I'll show you two different ways to go about this. Okay, there's no numbers given, but we can still get to an answer. Well, we know that Ohm's law says this, V equals IR. Now, a lot of you will say, okay, well, if the resistance increases, then that means that the current must decrease. Okay, that's only going to be true with this part. You have three variables in here. You need to know how two of them behave to see how the third is affected. It's a constant voltage, okay? So, since it's constant voltage, if V does not change, that's my symbol for stays the same, does not change, and R goes up, then very obviously, in order to make sure this equation still works, I must go down. If this side doesn't change, but this goes up, I must go down. And from the equation for power, again, if the voltage doesn't change and I goes down, power goes down as well. So more resistance decreases the amount of power because it decreases the current in there. And remember, current is one of these big factors that helps determine power. Another way to do this is just to use the power equation that looks like this. P equals V squared over R. Very clearly, if R increases, V stays the same, and the power decreases. Okay, so if you didn't think to do this, you could just look at just the power equation. That also works. Okay, two examples with light bulbs to close this out. A person has two light bulbs. The first light bulb is 20 watts. Second light bulb is 40 watts. We're going to talk about what that means in terms of how you would know the difference between the two of them if you just saw them. Person first creates two simple series circuits, each consisting of a 10-volt battery and one of the light bulbs. We're going to compare the currents in each circuit. So here's what we got. It's a very simple series circuit. There's our bulb. Okay, it's a 10-volt battery both times, and we're using either a 20-watt or a 40-watt light bulb. Comparing the currents. All right, we have the power for both, and we have the voltage drop around the light bulb. So what we're going to need to do is use this equation, P equals VI, to find the current in both. For the 20-watt light bulb, it's a 10-volt drop times I. The current must be 2 amps in the 20-watt bulb In the 40-watt bulb, on the other hand, the current is 4 amps. So notice, everything else being the same, the one that has a bigger power has a bigger current as well. And since we now have the current and the voltage, we can find the resistance. I guess we could have found the resistance before using a different power equation, but either way. You can kind of compare now that we know the currents, we can see how the resistances compare. Since it's the same voltage difference for both, we see that the higher current comes from the bulb with the lower resistance. Yeah. All over the place right now. So in other words, bulb with higher power, or let me do this first. Since same V, bulb with the higher power is more current. And therefore, lower resistance. We're going to build this real quick in the simulation. So I'm going to get a battery. I'm going to get 2 batteries actually. They're both going to be 10-volt batteries. Let's check values, conventional. Okay. All right, same thing over here. All right, these are going to be connected to bulbs. There's our bulb. This resistance, this is going to be the, let's see, this will be the 5 watt, or 5 ohm, excuse me. This will be the 2.5. There we go. Certain amount of brightness there. Aha. Okay, so let's move this whole thing down. And let's see which one of these is brighter. To me, they're both pretty bright, but it looks like the one on the right-hand side with the lower resistance, and we can go and check the currents too. Yep, current of 2, current of 4. The one with the higher current and the one with the lower resistance ends up being a brighter bulb. And if you remember, that was a brighter bulb, or what distinguishes that bulb is that it has a higher power rating. So the conclusion here, and this is more important if you get into some of the higher AP classes and you start talking about electricity more. Which bulb is the brightest? Explain your answer. The brighter bulb is the one that has a higher power rating. In other words, the 40-watt bulb. Okay, last example. 2 different light bulbs with known resistances are connected in parallel with a 15-volt battery. So we're dealing with parallel circuits now. Okay, here's our 15-volt battery. Can we see that? Yep, okay. Remember the definition of parallel, there's multiple paths. All right. Resistance of the first bulb is 60 ohms. Resistance of the second one is 150 ohms. Equivalent resistance of the circuit. It's parallel, so remember the equation is Req. 1 over Req equals 1 over R1 plus 1 over R2. This is going to be 1 over 60 ohms. Don't forget the units and make sure you're putting these in the right spots. Plus 1 over 50 ohms. So I'm going to do 1 divided by 60. Plus, parentheses, 1 divided by 150, and parentheses, plus, take the inverse, I get an equivalent resistance of 42.86 ohms. What is the total current in this circuit and how much current goes through each of the bulbs? So we're going to have to figure out 3 things. There's a total current coming out of the battery, and there's a current for each of the bulbs. Now that I know the equivalent resistance, I can figure out the total current pretty easily because Ohm's law applies to the circuit as a whole as well as the individual resistors. The total voltage for the circuit is 15 volts. That's the potential difference. Total current is what we're looking for. Req is that 42.86 ohms that we just found. I find that the total current is 0.35 amps. You can check me on that. Oh, okay, now that we know, let's see, we know the resistance and the voltage drop for each. We know the voltage drop for each is 15 because it's a parallel circuit, and that's how voltage drops work in a parallel circuit. So I'm going to call this one 1, I'm going to call this one 2. V1 equals I1 R1. 15 volts equals I1 times 60 ohms. 15 divided by 60 is 0.25 amps. Kind of makes sense. Most of the current goes through the bulb with the least resistance. Not all of it goes through that one, but most of it does. The currents balance themselves out so that the total voltage drop is the same. And just looking at those two, since the sum of the branch currents must equal the total current, you could probably take a good guess that this one is just going to be the difference between these two, so 0.1, but we're going to make sure the math works out. V2 equals I2 R2, and again, the 1s and 2s aren't necessary, but they help me keep the bulbs straight. This will be a 15 volt drop. I2, 150 ohms, 15 divided by 150 is 0.1 amps. Which bulb has the most power and is therefore the brightest? We can find the power by taking the voltage and multiplying by the current, or by doing a slightly more complicated calculation with the resistances using the one of the other equations for power, but I'm going to stick with this one. 15 volt drop times, let's see here, the current was 0.25 for the first one. 3.75 watts. For the second one, we have a smaller current, so we anticipate a smaller power. And just like before, we see that the bulb with the smaller current the bigger current ends up being the brighter one, because remember, power is not equivalent, but power tells you the brightness, okay? More power for a light bulb means it's more bright. The 60 ohm bulb is brightest. And just like we saw, like I said, smaller resistance, brighter. And I'll show you this on the simulation in just a second. If the brighter bulb is shined for 4 minutes, that's this one, how much energy would it dissipate? Since power equals work divided by time, the work done or energy transferred is equal to the power multiplied by the time. The power is 3.75 watts multiplied by 4 minutes. The time, so let's see, 4 minutes is 60 seconds each. So 4 times 60 is 240 seconds. We needed to convert to seconds because watts is joules per second. Can't be mixing minutes in there. We find that the work done, the energy transferred, is 900 joules. That's how much energy it gives off. And like I said, I'm going to build this for you real quick. So let's see, we're going to have a 15 volt battery. There we go. Conventional current. Let's do labels. Why isn't this focusing? There we go. All right. There's our light bulb. And since the light bulb can't go up to 150 ohms, what we're going to do for the second one, we're just going to put 2 light bulbs together that are both 75 ohms. Okay, and let's change the voltages. This one will be 60. Excuse me, not the voltages, the resistances. And we're going to do 75. And another 75. All right, so as far as the power goes, we wanted to know which one was most powerful. We see that very clearly the bigger lines are coming off of the, and there's more of them, coming off the 60 ohm bulb as opposed to the two 150 or 275 ohm bulbs. Even if we combine them together, the one on the left seems more bright. And just a quick check of the current. Total current 0.35, current in here 0.25, current here 0.1, just like we saw. Power calculations at this point are very straightforward, okay? It's real, I want you to associate with power with how much energy is being given off per unit of time. For light bulbs, that basically means brightness. For resistors, that means how much heat they're giving off per unit of time. That's pretty much it for power. The calculations are very straightforward. Those are the concepts I want you to have in your head. The last electricity topic we will have, it's magnetism. We'll have that when I come back.